So good evening, Ma'am Laredel Tamayo. So this evening I will be presenting our code and these uh, applications that was used in our code. So problem statement. In this project, we developed a classic Tetris game using Python. The challenge was to manage the real-time movement and placement of blocks within a grid while ensuring a smooth gameplay and accurate collision detection. Tetris is more than just a game. It is a problem of spatial logic, timing, and efficient state management. Data structure and algorithms, these are essential for solving these challenges. Arrays manage the grid, while algorithms handle line clearing, shape rotation, and collision detection. Dsa helps us write code that is efficient, reliable, scalable, skills that are crucial not just in games, but in almost every area of software development. So we took the time to develop this project to the full extent, using the DSA implementations that was discussed, throughout our session of teaching, and we made sure to have access or implement not entirely but almost all of the DSA concepts that was discussed in our code. So solution overview, program features, real-time single and multiplayer gameplay with synchronized status update. So uh, players can interact with one another either in a solo queue or in a multiplayer queue, 1v1. So dynamic piece control, rotation, hold, hard drop. So yeah, you have control over the blocks and score tracking with live score board updates. So we are capable of tracking and updating in the scores and reviewing who are the players that are on the top and at the bottom. So lobby systems with matchmaking and readiness status. So we have a lobby system which allows us to keep track of who are the available players within the game. So a in-game chatting system for players. So our players are capable of chatting real time. So if they want to have an interaction with others, data structures and algorithms that are implemented. These are concepts. Those are arrays, lists, stacks, FIFO, queues, FIFO, linked lists, binary search trees, sorting, and searching. So purpose in program represents game board shapes and queues. Handle hold block feature, handle of the next queue blocks, stores chat in the lobby, store and search player names, sort leaderboard for top players, search scores by username. Why chosen? It's easy to use and flexible, simple and last first out logic for the next block to be in smoother phase through using FIFO. Maintains message order with fast inserts, keeps score sorted and easy to look up. Quick searching and searching in BST. So So I provided today the following snippets of our code. No? So array list. So we use 2D list to model the game board, where each row is a sublist of tiles. This structure makes it easy to update the board during gameplay and check for collisions. The Tetris piece shapes are also stored as nested lists, so which allows simple rotation and transformation. Lists are ideal for this use case due to their dynamic nature and ease of access. So this code right here allows us basically to develop the shapes in general. So see the following, the for example, this O right here, this creates the square piece in our game. No, so basically the block that you can use in the game. So stacks LIFO. So the feature works like a stack where the current piece is pushed into the stack and retrieved later. Now, using the Python list, append adds a piece and pop and retrieves the most recently held one, aligning with LIFO logic for intuitive piece swapping. So the in-game example I can provide is that when you have a so let's just say you have a piece that's about to drop off, and then so by using shift you can put a block in a placeholder. You can see the placeholder on the right side in our game that I will be showing later on. So as you put your block in a placeholder, you can replace the current block that's about to fall off with the block that's on the placeholder. So while doing this, we are applying the stacks or the LIFO concepts, in this a in our code. So stacks or FIFO. So this code snippet is a queue for FIFO queue because it manages the next blocks of Tetris every time the next piece is placed or input. It will be removed in the list of three, which is DQ, and adds a new piece in the end, which can be called InQ. And with that, it follows the first in, first out principle. So as you can see here, based on our code and the in-game run screenshot. So we have three blocks. So let's just say the first two blocks gets dropped and removed, and let's just say the Z block goes to the top, which uh, is then the first one, while the two boxes remain empty. They will be again filled with a random block, which is one, which will be random, a random placement. So it applies the stock or FIFO logic because the first one at the top shall be dropped and will be the first one to be outed in in the box, which applies the FIFO logic in our code. So the binary search tree and searching and sorting. So right here we have the code snippet of the binary search tree. So we can see the class BST node, which will be which will be to track the username and scores, to identify the username and score. So and then the def insert, which will be fun to know who are the players that entered the game and the scores. And then we have the def search tree, which identifies uh, the the users and their current score. So the def in order allows us to keep track of the amount of players that have played the games and their score. So the last pick is the sorted scores self that leaderboard in order. So this allows us to basically put the players in ascending order based on the scores that they have to determine who's at the top and who's at the bottom. So we use the binary search tree for searching the players in the leaderboard. For searching and sorting, we used it for the high score uh, players. So here are the screenshots of our game and their applications with the DSA implementations that was discussed a few minutes ago. And that would be all. Thank you very much.